And welcome back to Mechanical Systems Design. In this video, we'll launch Project 4. And Project 4, this will be the last project in our course, and it really brings together everything that we've learned this quarter. So let's take a look at the project description. So we're calling this Furiosa versus the War Boys. And you're going to work with a team to design a robot that will pull as large a load as possible. And you'll test it, take video, upload some test data to a survey, and provide a brief written report that'll summarize your design. Our learning goals here, we have some new and some advancements. So the first thing is to apply this design approach that we've been using in the context of a more complicated system and in a team setting. The second thing is that we'll be trying to incorporate multiple custom designed components and catalog components into an assembly, which, as we'll see, brings some new challenges. And then finally, we're going to try to utilize more sophisticated motor and gear models, power analysis, and mass efficient component design. It's going to be challenging, but a lot of fun. Before we get started, it's probably a good time to just do a quick check of your materials. In addition to the motor and gearbox and power supply we used in the last project, make sure that you have your shafts and bearings and those longer electrical wire leads that we gave you, which you'll need for this project. So what's the task here? You're going to design a robot, which will go here, that will be connected to a big payload. And your robot's going to try to drag it across the floor, and you want to try to make that payload as big as possible. So the payload will comprise a book, like a textbook or something, with heavy stuff sitting on top of it as much as you like. And then you'll harness it to your robot, say with a rope. And this is just an example of how you could do that. And then your robot will have to pull the payload 1 meter in 3 minutes or less. And the bigger the payload that you can pull that distance, the better. You can do this on any floor that you'd like, as long as both the payload and the robot are on the same floor. And the title of this project is, of course, inspired by the 2015 movie Mad Max Fury Road, starring Charlize Theron as Imperator Furiosa. And in this scene, her rig is getting harpooned by the war boys that are trying to slow her down, but it's a well-built machine, and she outpulls them. Your robot will be made out of the Tamiya planetary gearbox kit and motor. That can be the only power source for your machine. And you can use those shafts and bearings that we provided. You can also add as much weight as you'd like to sit on top of your robot if you'd like, although it shouldn't be a structural component of your system. And that's really all of the catalog components that you should use in your design. You should make your custom parts with your personal 3D printer. And you can, of course, make repairs or little tweaks using lo-fi prototyping materials like hot glue and popsicle sticks and that sort of thing. But that shouldn't be the primary means of fabricating your robot. All right, we've done a little bit of failure testing of the Tamiya gears, and we provide some information there in case that's helpful. And we've also given you a starter CAD file for making custom gears if you want. These are optional, and the instructions for how to use them are in here. Some quick design tips as you get started. You probably can separate out the tasks of choosing motor set point and overall gear ratio from motor speed to robot forward speed from the task of designing the chassis and the mechanical structure at first. Of course, at the end, all these things are all interrelated, but it can be useful to separate those things out at first. And keep in mind that when you're testing your robot, eventually you may want to test lots of payload values in rapid succession, which could contribute to motor overheating. So take that in consideration when you set your motor operating point and factor of safety. As you have seen in this course, free body diagrams are just incredibly useful for machine design. And that will be especially true in this project. And I would encourage you, I think it'd be really helpful if you start out very early on with a good free body diagram of the whole robot plus payload system, the whole robot itself, the motor and gearbox just as one body, and each element in your transmission. And if you really understand what's happening in each of those free body diagrams, it's probably extremely useful tool for making some good high-level choices in your design. Just a note, apropos of nothing, mass efficient parts happen to use less material and thereby print faster. So that could come in handy. When you're trying to fit your machine together, press fitting and gluing can be a great way to, say, put the shafts and bearings in. To get the press fit just right, it can be really useful to print a really small test part with maybe a few different sizes of holes, so you can find the hole size that gives you just the right, so you can, it's not loose in there, but it's not too hard to press it in. Super glue is a great way to attach multiple components together for rigid joints, and it can be used to, say, attach rubber bands to the surface of a 3D printed part to increase its coefficient of friction if that's desired. The Tamiya kit comes with some machine screws and nuts that you can use to connect the gearbox to your custom components. Those work really well. And of course, you can use hot glue and all that stuff in an emergency, but those approaches generally are not great for precision, fine details, connecting catalog components, and that sort of thing. All right, so we have assigned you teams, as I mentioned, in order to make sure that we've got balance in the teams in terms of backgrounds, and to try to best meet people's schedules and desired teammates. That you and your team you are together. You are a set for this project. And so if you're going to succeed, you're going to need to work together really well. And based on the experiences we've had so far in the course, I think that definitely won't be a problem. But here's some tips about how you can make this a most effective collaboration. So one thing is to try always to be productive, proactive, and positive in how you give feedback to your teammates. Always kind of being respectful and looking for the way forward. Make sure you stay in good communication. And sometimes that's going to mean saying that you didn't get done what you had planned. That's okay. Don't be anxious about it. It's much better than not telling people what's going on. Make sure you attend the meetings and respond quickly to messages. Take on your fair share of the responsibilities in the project because your teammates are counting on you, but not too much because your teammates are entitled to their creative input and even to struggle with the material just as you are. And no one person can do the whole project by themselves, so you need to work together. Try to allocate the types of work evenly. So you wouldn't want one person doing the report and one person doing the design. That wouldn't make sense. You want to make sure everybody has a substantial role in each major aspect of design and in reporting, so that there's intellectual continuity through the project and in how it's explained. All right, so your team should have a kickoff meeting, and you should do that really soon because you've got a lot to talk about. And in that kickoff meeting, we'd like you to talk about goals, roles, meeting times, messaging, and team name. So goals, what I mean is your team, for example, trying to win an award? Are you all just want to go for it? Or maybe your team is most excited about learning a particular new skill set, and you'd like to take an approach that maximizes the learning that happens there. Or maybe your team is just wants to pass and get credit and move on, and that's okay too. But the important thing is that you have a discussion about this right away, and you agree on one set of goals for your entire team. And that almost always requires some compromise. If you really wanted to go for the award, but your teammate just wants to pass, the two of you are going to need to meet in the middle on that. Because you can't be successful if you have different goals. And after you come to an agreement as a group, stick with it. The second thing that you'd like to talk about is roles. Who's going to lead the motor analysis, who wants to lead the transmission design or chassis design, things like that. And remember, everybody should have a substantial portion in design and reporting. You should set some meeting times, especially this first week or so. Eventually we'll have some coaching session time dedicated to you working with your teammates. But in this first week-ish, we'll have a lot of topic readings and that sort of thing, and that'll use up a lot of the coaching time. So set some separate times to meet and discuss this stuff so you can get a good start. You'll also want to set up a good way of communicating with each other asynchronously, and you want a team name. And clever names are always appreciated by everyone. Now, this is a team project, but each of you will fabricate your own robot. And we do this because it's so important to your understanding of what's happening, to be able to hold on to this robot and see how it moves and feel how it behaves, and to do those tests on it yourself. So what we'll do is everybody in the team will create their own robot. They can all be exactly the same. And then we will use the average of your performance scores to set the team performance grade. And the way that's going to work is we'll have these two components. We'll have a nominal score and a payload mass-based score. The nominal score will just be full credit if you design a robot that moves. So even if the payload it can pull is approximately 0, full credit for the nominal score. And then the second portion is based on how large of a payload it can pull compared to big and small payloads, which we'll set later. If you want to go for it, there are some great design challenges, including, of course, the largest payload pulled, but also manufacturing excellence for a really well-built design, and also best style, which is open to your interpretation. So have fun with it if you like. And best summary report. So the summary report, this case, will be 5 or 6 pages, depending on how many team members you have. And the first page will be just photos. So we'll have your team name and teammate names, and then images that show all the important features of your robot. And you should be sure to include at least one image from every team member's physical robot. The next page will be a summary page where we'll have the description and reasoning, in this case, 500 words. And again, we're looking for really clear, convincing, edited, prioritized communication about what your design is and why those choices make sense for this challenge. And you should also list a few things, the choice of applied voltage and motor to robot speed ratio, and your estimates and actual measured values of the current, pull time, and payload. The next page will be on your transmission, and especially specifically, we'll talk about the process you used for choosing the applied voltage and total gear ratio. And for that, you can use equations or figures generated by code as you like, as is helpful, but it's not required. And another element in that transmission page will be the power flow. So for every watt that came in from your power supply, where did it all go in different energy sinks in your system? And finally, we'll have component pages. So for each of the most critical custom designed components in your system, and where we have an equal number of component pages to the number of team members in your group. So each team member should lead one of these. You'll have one page, and you'll have the byline, who led that page, an image of the part somewhere in there, a description and reasoning section, back of the envelope analysis that you used to make that component effective, and any finite element analysis that you used to make that component effective. And the final thing that we'll do here is have a self and peer evaluation, where you'll report in a brief survey your perceptions of your own contributions to the project and ease of collaboration, and the same thing for your teammates. And the overall project grade will be 30% based on that objective performance, 60% on your report, and 10% on peer evaluations. So this is it's a big project, but it's a lot of fun. And I really enjoyed working on this in the last week or so. And I think you're gonna enjoy it too. So have fun with it, and good luck.